Hello everybody, welcome to the discussion on Introduction to Geometric Tolerancing. So in this video, what we're basically going to do is talk about geometric tolerance. So I will give a brief overview of why geometric tolerance is useful, where it actually comes about, and then we'll discuss some of the commonly used symbols in geometric tolerancing. So our learning outcomes for this video is going to be to introduce you to the concept of geometric tolerancing, as well as discuss some of the basic geometric tolerance and their symbols and what they actually mean. So let's quickly discuss why is it that we actually need a geometric tolerancing. So imagine you're a designer and you decide or think about a super awesome design. So you have this bolt over here, and then you imagine this actually goes in and then secures these two parts. So in reality, nobody can actually make a perfectly straight hole or a perfectly straight bolt. So this is obviously an exaggeration here, but imagine just for the fun of it, our machine shop guy is like, yeah, you know what? I don't really like Professor Vijay Raghavan. I'm just going to mess with him and then make something like at a really weird angle here. So now, if I try to assemble this together, there is no way on earth this is actually going to fit. So I go back to my machinist guy and they're like, what the hell did you make, man? And then he's going to tell me, you never said any restriction on the shape. So you gave me a dimensional tolerance. Here, go measure the vernier with the vernier. And then you will notice that everything is actually within the spec. There isn't anything you can do at this point, except maybe like kick yourself and teach yourself geometric tolerance. Obviously, this is more of a made-up example, but this actually stems from some real-world example back during the World Wars, where the US would ship a bunch of parts which were only set to the dimensional tolerancing, so their sizes would be fixed. But when the mechanics and people at the field try to assemble them, they notice that because the shape wasn't actually didn't have any tolerance, the parts wouldn't actually assemble together. This is where the concept of geometric tolerancing was developed, and this is where our story ends and we come to the present day. So the first symbol we're going to look at is known as the flatness symbol. This actually measures how flat the surface is actually going to be. So the symbol is actually a parallelogram here. So this is the symbol. This is for the parallelogram, is the symbol for the flatness. So what does it actually mean? So I'm going to imagine there is a surface. I'm going to switch. So I'm going to imagine this is my surface, awesome surface that I'm trying to make it like absolutely flat. So I'm basically going to figure out that this is the surface, I want it to be flat. So if I actually zoom into the surface, you'll notice that it'll actually have a little bit of bumps and this way and a few bumps the other way. This is what this figure is actually trying to show here. Then if I have a flatness and I give you a tolerance, what I'm basically saying is that all the bumps in all directions need to lie within that tolerance band. That's what is meant by the flatness symbol. So generally, if you wanted to make this surface flat, so we wanted this surface to be flat, I'm going to pick a perpendicular surface. Look at the right view here. This would be the corresponding surface here. If I wanted to make this flat, I'm going to mark off using this symbol here. That basically tells me that I'm marking off that particular surface, and I put the symbol right here, and then I put the tolerance right here. So that gives me the tolerance. So there are multiple ways I can do it. I can either kind of extend it like shown here, or what I can actually do is I can actually go do kind of like have an arrow here and then point it down as well. So these are two different ways in which you can actually show the flatness of that particular drawing. Once you actually define the flatness, you add a label to it. So rather than each time referring to the surface as the surface which is 0.01 millimeters within tolerance, I'm going to call it surface A, and then we'll see where this comes in handy in the next step. So the next symbol we're going to look at is known as the perpendicularity symbol. So this is obviously, as the name suggests, you're going to say that this surface is going to be perpendicular to the bottom surface over here. So that basically means I'll use a perpendicularity symbol. Same way the surface here is going to be perpendicular to both the surface here as well as the surface here. So we could potentially use a perpendicularity symbol to give the tolerance band here. The symbol itself is going to be this perpendicularity symbol, which is kind of like straightforward as you would normally expect. So that's going to be this symbol over here is the perpendicularity symbol. And obviously the perpendicularity needs to refer to some other phase. That's where our previous label comes in. So the usage, so I'm going to pick a first surface. In this case, I'm going to pick the bottom surface and then I'm going to make it or give it a flatness reference. So once I have that, I can kind of like set this up on a reference axis and then start measuring. So what I'm going to do is actually give it a label here. So notice that I can put the label either here or here as long as it's somehow connected to the surface. Everybody in the world would know that this is the surface I'm referring to. So if we come back here in our basic shape, what I basically done is I basically called the bottom surface here. I marked it out to be flat. So once I have that to be flat, I'm going to pick another surface here, basically the side surface, and then I'm going to make it perpendicular. Obviously, it doesn't make any sense if I say a surface is perpendicular. It needs to be perpendicular to some other surface. So this is where we put in the reference surface over here, and then we're going to say that the right surface here, beg your pardon, the left surface here, the surface here is going to be perpendicular to the bottom surface. So that's what we're doing with this particular example. So once we have that, we can potentially label this with the letter B. So it is on purpose that I put the labels at different locations. So all of these are acceptable conventions. So you can either have an extension line and then put the symbol within box, or put an arrow and then give the actual perpendicularity or a parallelism symbol, and then you can attach the label either here or to the side as shown here. So moving on. So what if we make both the surfaces to be flat? Would that actually give me the perpendicularity? So let's think about it, right? So if I make both surfaces flat, does it actually automatically give me perpendicularity? So you can imagine that I can have a case where they are flat. So this line is completely flat, this one is completely flat, but they're not perpendicular to each other. So just to recall, or things to keep in mind is that perpendicularity automatically implies flatness. So this basically implies flatness. So not the other way around. Right. So perpendicularity implies flatness of the surface, but flatness does not automatically imply perpendicularity. So what does it actually mean? So essentially, I've defined a basis line, which is going to be kind of like an imaginary virtual, like the average point, and then I'm going to basically draw two vertical lines, which is going to refer my bound. Based, if I give a 0.01 tolerance, that means this distance is going to be 0.01, and my side surface can lie anywhere within those two bounds, but it needs to be completely within that bound that I've shown. So let's imagine this table over here and then think about what might be my application. So if I imagine this table, the top surface here, I might want it to be reasonably flat, but the actual height of the table, I may not be super concerned. Like I still want to give a dimensional tolerance, but the variation in this height, I may not be super concerned about. So in that case, what's going to happen is I can give a dimensional tolerance of maybe like 1 millimeter on the overall height, but my flatness would typically be 1 order or 2 orders of magnitude more stringent. So the next symbol we're going to look at is known as the circularity. The symbol is obviously just a circle. So the way this would go is you're going to basically say put a circle and then give the tolerance in the box beside it. So what does that mean? So if I have an arbitrary shape, I'm going to want to bound it between these two dotted lines, and the distance between those two dotted lines is restricted to 0.01. So that's what this circularity symbol actually means. So if you had a cylinder, what this will actually mean is if I have a cylinder like this, so the bottom is here, the top is here, this is a cylinder. So what I'm basically going to do is take one cross section here and then check if the circularity is maintained. I'll potentially take another cross section here and then check if the circularity is maintained and so on. So that's what this circularity means. I'm not actually looking to see if it's a proper cylinder. Rather, I'm just focused on individual cross sections of that shape. Moving on, if we actually wanted to enforce the cylindricity, we use the cylindricity symbol, which is basically a circle with two tangential lines as shown below. So what that actually means is I'm actually trying to bound the entire shape within two concentric cylinders. Parallelism is used to ensure that two surfaces will be parallel to each other. So if I go back to my yellow block here, I can potentially say I want the bottom surface here to be completely flat, and then I'm going to make the top surface to be parallel to the bottom surface here within whatever tolerance that I specify here. So as before, parallelism will imply the flatness of the top surface, but the other, it's not true the other way. Now we are going to come to the most important tolerance that is very commonly used in all of the engineering drawing. So this tolerance is known as true positional tolerance. So this is typically used to specify quote-unquote true position or location of cylindrical features like holes and pegs related to three reference surfaces. So this is how it's going to look. So essentially the typical symbol is going to have basically typical symbol would be some diameter is going to be 10 plus minus 0.1. And then you're going to have this bullseye symbol, which is going to be the true position symbol. So this bullseye symbol is the symbol for the true position. And then you're going to basically say, I'm going to give some tolerance here. The diameter symbol basically means that I'm defining the tolerance as a cylinder rather than a distance. And this letter M basically means that it's only enforced at MMC. So that is basically at MMC. And basically the three reference surfaces that I set is going to be A, B, and C here. So if I go back to my yellow block, so I have this block here. So I'm going to imagine there is a hole that I'm going to make here on the top surface. So maybe I'll just draw the cylinder circle here. So this is going to represent my hole through the object. So when I do that, what I'm going to do is basically define three perpendicular axis reference. So when I'm doing the axis, I can't actually choose my neighbor's reference, or I can't choose like a global X, Y, and Z coordinate system. So I need to basically define an axis in the object itself. So that's where our three reference surfaces are going to come. So for this surface, this is where my hole is. I'm always going to pick the face on a face on which the hole would be made. So if the hole is going through, so I'll have the hole at the bottom surface here as well. So I'm going to have the hole at the bottom surface here as well. I'm always going to choose this surface which is perpendicular to the axis of the hole to be my first reference. So that's going to be my reference A. And then I'm going to define a reference B, which is going to be this side, and the reference C on the back side. So this basically what it does is I'm basically defining a coordinate surface, coordinate reference on the shape here. So basically 3 faces you can see are going to be my 3 reference surfaces. I'm going to have one face here, one face here, and one face here, which defines my 3 perpendicular planes that I can use as my reference starting point to define the true position of the hole here. So the hole itself could kind of move all over the place. The axis can be anywhere it wants, but once I specify the true positional tolerance, that means with respect to these 3 axes, my hole is fixed within a tolerance band. So that's what this basically refers to, and we are basically enforcing it at maximum material condition. So what that basically means is the dimensional tolerance is going to allow the hole to either change like so, or it can be like a star or a weird shape. And once I have, for each cross section, I can find the center here. So for each cross section, I could potentially find the center point here. And then this might be another cross section where I find the center point here. I'm basically going to join all of the center points using this axis line like this. So this is going to be the line that joins all the center points. And that basically needs to be within the tolerance band. So if I just quickly switch back, the tolerance I said was 0.05. So what that means is this cylinder has a diameter phi of 0.05. And because our units are going to be in millimeters, so this would be 0.05 millimeters here. So that's what I'm actually referring to when I'm basically saying my tolerance here in the previous step. Previous page is phi 0.05. And then basically these cylinders are kind of like stacked up at the maximum material condition. So to understand this, we would actually do an example or an exercise where you have these different cylinders where you can actually find the center axis, measure the deviation from the center axis, so that will give you the cross section, as well as figure out how well the center axis itself is bound, which will give you the geometric tolerance. So this I'm going to refer you to the next video. Thank you. So to quickly recap here, what we did was we basically talked about where the concept of geometric tolerance comes from, and then we discussed how geometric tolerance would be useful when you're defining or kind of like restricting the system, and how is it that you're going to enforce the flatness, the perpendicularity, and we kind of briefly introduced the concept of true positional tolerance.